Good morning, everyone. This is an audio lecture for visually impaired students, and in this lecture, we are going to discuss about S block elements. Alkali metals, group 1 elements. The group 1 elements has n as 1 electronic configuration and are highly reactive metals. Group 1 includes lithium, sodium, potassium, rubidium, cesium, and francium. Physical properties of alkali metals: atomic size, largest in their respective period except noble gas element. Size increases from lithium to cesium due to addition of an extra shell. Comparison of atomic size of group 1 and group 2 elements. Atomic size of group 2 is smaller than that of group 1 because on moving from left to right, size decreases. Oxidation state. The group 1 element exhibits +1 oxidation states. Ionization energy. The first value of ionization energy for the atoms in this group are lower than those for any other group in Hall periodic table. Second, ionization energy of alkali metals is very high because by losing one electron they achieve inert gas configuration. Density. Alkali metals have large size which accounts for their low density. As we know, density is equal to atomic mass by atomic volume. Atomic mass increases from lithium to cesium in the group and volume increases, but increase in atomic weight is more than increase in volume. Therefore, density increases from lithium to cesium. Melting and boiling point. Melting and boiling point of alkali metals are low due to weak interatomic bonds because of their large atomic radii and presence of only one electron. Electropositive character. Electropositivity is inversely proportional to ionization energy. Alkali metals have the tendency to lose the electron. Now we will discuss about conductivity. Due to the presence of loosely held valence electrons which are free to move in metal structure, these elements are good conductor of heat and electricity. Nature of bonds. The electronegativity value being low, they combine with other elements to form ionic bond. Flame test. First group elements and their salts give characteristic color to Bunsen flame. By flame energy, electron of outermost shell get excited, which on returning back to the ground state releases absorbed flame energy as a visible light. The energy is minimum in case of lithium positive ions and increases in order: lithium positive, sodium positive, potassium positive, rubidium positive, and cesium positive. Lithium gives crimson red color, sodium gives golden yellow color, potassium gives violet color, rubidium gives red violet color, and cesium gives blue color. Electronegativity. The tendency to attract electron is low as the alkali metals are electropositive. The electronegativity thus decreases from lithium to cesium as the electropositive character increases. Specific heat. The specific heat decreases from lithium to cesium. Heat of atomization. Heat of atomization decreases from lithium to cesium. Hydration of ions. The ions are highly hydrated. The smaller the size of the ion, the greater is the degree of hydration. Thus, the degree of hydration decreases down the group from lithium positive to cesium positive. Thus, with the increase in hydration, electrical conductivity decreases. Lattice enthalpy. Salts of alkali metals are ionic solids. Lattice energy of salts of alkali metals having common ion decreases on decreasing down the group. Photoelectric effect. Potassium, rubidium, and cesium. Photoelectric effect. Potassium, rubidium, and cesium have quite large atomic size, so their ionization energy is very low. Due to very low ionization energy, their valence shell electron gets excited even by absorbing visible light. That's why cesium is used in photoelectric cells. Reducing character. Alkali metals are strong reducing agents. Reducing character increases down the group. Properties of alkali metals. They are very soft. Alkali metals can be easily cut with a knife. Among the alkali metals, lithium is hardest. Electronic configuration. They have one valence shell electron. Electronic configuration is ns1. Atomic size. Size increases down the group due to added of extra orbit. Electropositive. It is the ability to remove an electron. Electropositivity increases down the group. Cesium has the highest electropositive character. Stored in kerosene oil. Alkali metals react with air easily to form oxide layer, therefore they are stored in kerosene oils. Reaction with water. They reacts with violently with water to form hydroxides. Don't even dare to go near when cesium reacts with water. Reaction with ammonia. On dissolving NH3 forms ammoniated cation and electron solution turns blue as shown in the given reaction. Uses. Lithium is used as antidepressants, batteries. Sodium is used in street lamp salts. Potassium is used as fertilizers and cesium is used in atomic clocks. Now we will discuss about the reactivity of alkali metals. These elements are very reactive, so do not found in free state and nature. Reactivity is inversely proportional to ionization potential. Order of reactivity is cesium is highly reactive, whereas lithium is least reactive in its group. They have low values of ionization energy as and radially lose their valence electron to form metal ion. They have low heat of atomization and easily come into vapor form. They have higher heat of hydration. Reactivity towards air. Alkali metal gets tarnished in air due to the formation of oxide on their surface. Hence, they are kept in kerosene or paraffin wax. Alkali metals, when reacts with moist air, form carbonates. For example, Na plus O2 gives Na2O. Na2O plus H2O gives NaOH. NaOH plus CO2 gives Na2CO3 plus H2O. Reactivity towards oxygen. Alkali metals on reacting with oxygen form oxides. Then these oxides react with water to form hydroxide, and on reacting the hydroxide with CO2 they form carbonates. For example, M plus O2 gives M2O, M2O plus H2O gives MOH, MOH plus CO2 gives M2CO3. M2O plus O2 gives peroxide, that is M2O2. Normal oxides, monoxide. Na plus O2 gives Na2O. Peroxide. Na plus O2 in excess at 300 degrees Celsius gives Na2O2. Superoxides can also be formed. Superoxides are ionic oxides, that is M positive, O2 negative. M plus O2 in excess gives MO2, where M may be potassium, rubidium, and cesium. Superoxides are stronger oxidizing agents than peroxides. The stability of these superoxides is in the order Cesium superoxide, that is CS2, is more stable than RbO2, which is more stable than KO2. Stability of oxides. Normal oxides are more stable than peroxide and peroxides are more stable than superoxides. Reaction with hydrogen. Alkali metals combine with hydrogen forming ionic hydrides. Example, M2 plus H2 gives MH. Hydrides of alkali metals are attacked by water to give back hydrogen. MH plus H2O gives MOH plus hydrogen gas. Thermal stability. LiH is more stable than NaH, which is more stable than KH, which is more stable than RBH, and RBH is more stable than CSH. Basic property. Cesium hydride is most stable, whereas lithium hydride is least stable. Reaction with water. Alkali metals react vigorously with H2O forming hydroxide with the liberation of hydrogen gas. M plus H2O gives MOH plus H2. Reactivity with water increases from lithium to cesium. So lithium is least reactive towards water. Ne reacts vigorously. Potassium reacts producing a flame, whereas rubidium and cesium reacts explosively. Monoxide gives strongly alkaline solution with water. M2O plus H2O gives MOH. Reaction with dilute acids. Due to alkaline nature, these metals react rapidly with dilute acids and the rate of reaction increases from lithium to cesium because of increase in basic character. Carbonates and bicarbonates. Small size and strong polarization of lithium distorts the electron cloud of the nearby oxygen atom of large CO3 to negative ion to such an extent that CO bond gets weakened. Li2CO3 on heating gives Li2O plus CO2. Replacement of larger carbonate ion by a smaller ion leads to increased lattice energy and thus favors the decomposition. M2CO3 on heating gives M2O plus CO2 gas. Halides. All the metals in this group form halides of type Mx. Lithium positive is the smallest ion among alkali metals. It would be expected to form hydrated salts more rapidly than other metals. Properties. As evident from the following properties, alkali metal halides are ideal ionic compounds. All alkali halides except lithium fluoride are freely soluble in water. LiF is soluble in non-polar solvents. They have high melting and boiling points. For the same alkali metal, the melting and boiling point decreases regularly in the order fluoride, chloride, bromide, and then iodide. Now we will discuss about alkaline earth metal, that is group 2 elements. The group 2 elements have Ns2 electronic configuration. The group 2 involves elements beryllium, magnesium, calcium, strontium, barium and radium. Physical properties of alkaline earth metals. Atomic size. Smaller the ionization energy of group elements, since extra charge on nucleus attracts the electron cloud. Size increases gradually from Be to Ba. Oxidation state. The group 2 elements exhibit +2 oxidation state. Ionization energy. First ionization energy is higher than first group elements because of smaller ionic size and completely filled s orbital, that is stable electronic configuration. Decreasing order of ionization energy is Be has highest and Ba has lowest ionization energy. Second ionization energy is lesser than first group. Density. The size of group 2 elements are smaller than that of first group. Thus, these elements have higher density than group 1 elements. Density increases from Be to Ra. Melting and boiling point. Since the cohesive forces decreases down the group, the melting point of elements of group 2 decreases down the group. Exceptions. Magnesium has the lowest melting point. Boiling points do not show regular trends. They are harder than alkali metals. Electropositive character or metallic character. The atomic size is smaller than first group, so these are lesser electropositive than first group. Electropositivity increases from Be to Ba. Conductivity. These are also good conductors of heat and electricity due to presence of two free electrons. Nature of bonds. Be mainly form covalent compound. The rest of the elements in the group 2 form ionic bonds. Flame test. Ca gives brisk red color. Sr gives crimson red color on flame test. Ba gives apple green color, whereas Ra gives crimson color. Electronegative values. The electronegativity value of group 2 are low but are higher than the value of group 1. The value of electronegativity decreases down the group. Lattice energy. Lattice energy of salts of alkali metals having common anion decreases on decreasing down the group. Hydration energy. Lattice energy of salts of alkali metals having common anion decreases on decreasing down the group. Hydration energy. The hydration energies of the alkaline earth metal ions are 4 or 5 times greater than for alkali metal ions due to their smaller size and increased charge. Delta H, that is hydration energy, decreases down the group as the size of ions increases. Photoelectric effect. These elements do not show this property as their atomic size is small, hence ionization energy is higher than first group. Standard oxidation potential. Standard oxidation potential of alkaline earth metals is given below. This is a table in which standard oxidation potential of the alkaline earth metals is given. Now we will discuss about chemical properties of alkaline earth metals. Reactivity. They are less reactive than alkali metals. Order of reactivity is Be is least reactive and Ba is most reactive. Reactivity towards air. Except Be, these metals easily tarnished in air. Beryllium in powdered form burns brilliantly in or ignition in air. In most air except Be, all the elements converted into carbonates in moist air. In dry air, all elements of second group give nitride and oxides both. Reactivity towards oxygen. Alkaline earth metal react with O2 to form MO type oxides where M is Be, Mg, Ca, Sr and Ba. In second group only Ca, Sr and Ba form peroxides. Example CaO2, SrO2 and BaO2. BeO shows amphoteric property. MgO is a weak base, whereas CaO, SrO and BaO are strong basic in nature. Basic properties increases from BeO to BaO. Reactivity towards hydrogen. Except Be, all the alkaline metals form MH2 type hydrides on heating directly with hydrogen. BeH2 is prepared by action of BeCl2 with LiAlH4. BeCl2 plus LiAH4 gives BeH2 plus LiCl plus AlCl3. BeH2 and MgH2 are covalent and other are ionic in nature. Reactivity towards water. Calcium, strontium, barium, and radium decompose cold water readily with evolution of hydrogen. M plus H2O gives MOH twice plus H2. Magnesium decomposes boiling water, but beryllium does not react with water even when red hot. Its protective oxide film survives even at high temperature, and its oxidation potential is lower than the other members. Reactivity of alkaline earth metals increases on moving down the group as the oxidation potential increases. However, the reaction of alkaline earth metals is less vigorous than alkali metals. Reactivity towards halogen. All the group 2 elements combine with halogen at elevated temperatures, forming their halides. Metal plus halogens gives MX2 type of halides. Thermal decomposition of NH2. Thermal decomposition of NH4 twice BeF4 is the best route for the preparation of BeF2 and BeCl2 inconveniently made from the oxide. BeO plus C plus Cl2 at 600 to 800 Kelvin gives BeCl2 plus CO. Reactivity towards acids. The alkaline earth metal readily react with acids liberating dihydrogen. Reactivity towards acids. The alkaline earth metal readily react with acids liberating dihydrogen. M plus 2 HCl gives MCl2 plus H2. Diagonal relationship of Be and Al. Both do not impart color to flame. Carbides of both on reaction with H2O gives CH4. Both are rendered passive by concentrated HNO3. Oxides and hydroxides of both are amphoteric in nature. Magnesium, ores of magnesium, magnesite MgCO3, carnallite KCl MgCl.6H2O. Extraction of Mg is done by electrolysis of fused MgCl2, which in turn is obtained from carnallite and magnesite. Carnallite can't be used directly to get anhydrous MgCl2 by heating because all the water by crystallization cannot be removed by heating. Strong heating may change carnallite into MgO. MgCl2 plus 2H2O on heating gives MgO plus 2HCl plus H2O. Dose process. MgCl2 plus 6H2O in presence of dry HCl gives MgCl2, which on reacting with NaCl gives Mg. Compounds and uses. Magnesium. Salt cement MgO plus MgCl2 used in dentistry. Epsom salt MgSO4.7H2 used as purgative in medicine and modern days. Magnesia alba 3MgCO3.MgOH twice 3H2 is used in toothpaste and cosmetics. Calcium. Ores of calcium are as given below. For example, dolomite, that is MgCO3.CaCO3, gypsum CaSO4.2H2O. Calcium oxide CaO burn lime and quicklime. CaO plus H2O gives CaOH twice plus heat. Mortar which is calcium oxide plus sand plus water. Limelight. When exposed to oxyhydrogen flame, it starts emitting light called limelight. Gypsum or alabaster CaSO4.2H2O. CaSO4.2H2O on heating at 390 Kelvin gives plaster of Paris, that is CaSO4.half H2O plus 1 and half H2O water molecule. Plaster of Paris settles and becomes hard on cooling. Milk of lime. Suspension of CaOH2 and water is known as milk of lime. Cement. Cement is chemically calcium silicate plus calcium aluminate and 1% gypsum. Raw materials. Limestone provides CaO, clay provides SiO2, Fe2O3, and Al2O3. Approximate composition of cement is CaO is 50 to 60%, SiO2 is 20 to 25%, Al2O3 5 to 10%, MgO 1 to 3%, Fe2O3 is present in 1 to 3% amount. If cement has excess of lime cracks appear, excess of silica slow setting, less of lime weak cement, excess of Al2O3 fast setting. Cement with Fe is white cement. Setting of cement is exothermic process. Concrete, which is cement plus sand plus gravels. Mortar, which is CaCO3 plus and sands and 1:3. Reinforced cement, cement plus sand plus iron rod. Group first and 2 oxide. Sodium oxide. Preparation of sodium oxides. Na2O is prepared by burning Na at 180 degrees Celsius in a limited supply of air or O2 and distilling of the excess of Na in vacuums. The reaction is Na plus half O2 at 180 degree gives Na2O. By heating sodium peroxide or nitrate with sodium, Na2O2 plus 2Na gives Na2O. NaNO3 plus Na gives Na2O plus N2. NaNO2 plus 6Na gives Na2O plus N2. Properties of sodium oxide. It is a white amorphous mass. It decomposes at 400 degrees Celsius into Na2O2 and Na. The reaction is Na2O at 400 degrees Celsius decomposes into Na2O2 and Na. It dissolves violently in H2O yielding NaOH. The reaction is as given below. Na2O plus H2O gives NaOH, sodium peroxide, Na2O2. Na2O2 is formed by heating the metal in excess of air or O2 at 300 degree, which is free from moisture and CO2. Properties. Na2O2 is a pale yellow solid becoming white in air from the formation of a film of NaOH and Na2CO3. In cold water, 0 degrees Celsius, it produces H2O2, but at room temperature, it produces O2 in ice cold minerals acid and produces H2O2. Na2O2 plus H2O at 0 degrees Celsius gives NaOH plus H2O2. Na2O2 plus H2O at 25 degrees Celsius gives NaOH plus O2. Na2O2 plus H2SO4 at 0 degrees Celsius gives Na2SO4 plus H2O2. Magnesium oxide. It is obtained by heating natural magnesite and also called magnesia. MgCO3 gives MgO plus CO2 properties. It is a white powder. Its melting point is 2850 degrees Celsius, hence used in manufacture of refractory brisk for furnaces. It is slightly soluble in H2O, impacting alkaline reaction. Calcium oxide. Calcium oxide is commonly known as quicklime or lime and made by decomposing limestone at high temperature of about 1000 degrees Celsius. Calcium carbonate on heating gives calcium oxide plus CO2 properties. It is white amorphous powder of melting point 2570 degrees Celsius. It ejects intense light, that is limelight, when heated with O2H2 flame. It combined with some acidic oxide and have properties similar to basic oxide. For example, CaO plus SiO2 gives CaSiO.